Good morning. Good morning. Yes, my name is Sjoerd, Meijer. I'm co-presenting today with Sam Parker. Also in our team is David Green, but he's not attending this year. We are part of a performance solutions team. We look after performance issues, opportunities in our embedded toolchain. This is an embedded toolchain that mostly target the M-profile family of ARM processors, the microcontrollers. And this architecture got a new architecture revision that brought a vector extension to the M-profile, the microprocessors. So that's really exciting. That's what we're going to talk about today. If you're getting worried that this is all a little bit ARM-specific, don't you worry, it won't be. To efficiently support this new vector architecture, we had to solve quite a few, let's say, generic puzzles. So this talk is about what those puzzles are, how we solve them, our Clang and LLVM contributions, and how that might be interesting or useful for you. So first, I want to very quickly highlight the new Meijer MV architecture features. This is intentionally very, very light on details because, well, I don't have time to explain them, but also we don't really need it for this talk. So I'll just very briefly touch on these new extensions. The first one is low overhead branches, also known as hardware loops. I will refer to them as hardware loops from now. This is not really a new thing. Many architectures, DSP architectures, have this for many years already. And the idea is that you can accelerate loop execution with hardware. When you execute the loop, you have a loop test, you have a loop increment, and you have a branch that can be accelerated by hardware. In a nutshell, that works by setting up the iteration count, and then your hardware takes care of executing that loop body a number of times. The second one, the big one, let's say, is vectorization. Again, I'm not going into details. For this talk, it's enough, let's say, to think about this as a fairly normal vector extension. You have your vector load, your vector add and store, etc. The vector sizes is 128-bit. That's also very normal. Slightly different, though, is that it has only 8 vector registers. And the reason is that this is targeting microcontrollers. And they are a bit more, they can be less power, they need to be less power hungry than a bigger application course. So this is a trade-off here. It also has one predicate register to support predicated execution, which actually brings us on to the next big thing, predication. We have 2 forms of that, tail-predication and lane-predication, and we'll be explaining that in a moment. So I've just introduced these 3 big architecture features, hardware loops, vectorization, and predication, and this can all be combined. So what that means is we can, for example, for a loop, we can generate now a tail-predicated and vectorized hardware loop. Well, that's a lot of things. I see you thinking, what do you mean? So yes, we need to explain what it is, of course, why it is useful, and then we're going to talk about how we actually achieve that, how our transformation pipeline looks like to generate code for this. First, we need to explain a few things, starting with predication, and tail-predication is the first. When you vectorize code, you sometimes may need a scalar loop. If your iteration count of that loop is not a multiple of the vectorization factor, you need a few scalar iterations. Tail-predication removes the need for that. We'll go into more details later. The more simple one is lane-predication, probably best illustrated with an example. Shown on the bottom left. If you have vectors A, B, C, and D, you iterate over these vectors. Depending on a condition, you either store B plus C to A or B plus D. The more vector way of doing that is shown in the middle. It's vector pseudocode. Instead of doing this in the scalar way, they are now vector operations. So we have a vector compare. This generates a mask. So we do a vector compare of A plus B by element, and the result, the true or false value for that comparison is stored in a mask. So we have a set of true and false values. That mask is then consumed by the next statement. So for all the true elements, we now do B or C. And also that mask is consumed by the next statement. For all the false values, we compute B plus D. This literally translates to ARM MV code on the right. Ignore the syntax, it's not important. But this is now what we call a VPT block or lane predicated, this mask generates active and inactive lanes that are consumed by the next iteration instructions. And the first instruction generates this mask, and there can be up to 4 instructions using that to select lanes. For tail predication, that is a bit more complicated. So let's look at that with an example. Suppose you want to vectorize this loop, and when you play with auto-vectorisation, this is probably the first example that you write. You do a plus b, and store that to C. Assume that this loop is vectorizable, so you put either restrict on the arguments A, B, and C, or there are runtime checks to make sure that memories don't overlap. This allows vectorization. Then the main observation is that n is used as a loop count, but assume that n is unknown at compile time. This has the consequences that we need a vector body and a scalar remainder, and let's explain that too. Shown on the top left is now the corresponding vector code, and just for this example, let's assume that n equals 10, so we execute 10 iterations, and that means that we process 10 elements of the vectors. And then let's make a second assumption that we vectorize this with a factor of 4. And that means that we pack 4 elements into a vector. And so the vector operations work on 4 elements at the same time. You see this in the pseudocode there? That is what we call the vector body. This now iterates on the vectors. And since we pack 4 elements, we do 2 iterations of the vector body. And because we do 2 iterations, we process 8 elements, but we need to process 10 elements. So that's why we have the second loop, the scalar remainder, to execute those last 2 iterations. To explain what tail predication is, we do a transformation, which is called, the scalar remainder is also sometimes called the tail. Now, for tail predication, what we do is we fold the scalar remainder into the main loop. So tail folding creates 1 loop, but then the tricky business is that we need to execute 10 iterations. We need to process 10 elements, 10 iterations. But if you tail fold this loop, you need to execute 3 iterations of this vector body, and 3 times 4 would mean processing 12 elements, and that's what we need to avoid. So shown on the right-hand side is at the bottom is the last iteration of the vector loop. We need to make sure that we activate only the first 2 elements of that vector and disable the second part to process 10 elements. And that is achieved by the first statement in the tail folded loop, the get mask. Depending on the iteration count and the current iteration, it generates this mask to set active lanes and inactive lanes. Sam is going into more details. Once we have the tail folded loop, that is kind of the basis for everything. This is kind of the start to generate eventually a tail predicated vectorized hardware loop. This is the loop form that we are aiming at. And that allows us to generate this. This is the actual code that we would like to generate. Again, ignore the assembly code, it's unimportant. The main observation is that this is real code, only 6 instructions, 4 instructions for the loop body. It does 2 vector loads of A and B. It does a vector add for that and a store to C. And then we have only 2 instructions for loop control. The first one is a hardware loop, a while loop start, and TP means tail predicated. So we set up the number of elements to be processed, and then this takes care, kind of under the hood, to set the active, inactive lanes that I talked about in the previous slide. Now, the benefits of this should probably be obvious. This is very compact. There's not an instruction wasted on anything. So this is very dense code, which is what we want for microcontrollers. Code density is really important. Also, performance is also probably for performance. This is really good. For the microcontrollers, the data sets might not be so large. So the time spent in the scalar remainder might not be insignificant. So getting rid of that is a good thing. So this is also good for performance. Now, this is what we want. This very tight loop that combines scalar code and vector code. But a typical vectorization plan looks pretty different. Usually when you vectorize a loop, you first have a test if you execute the loop at all. If not, you bail. Second test probably is if the iteration count is a multiple of your vectorization factor. If it's not, if it is, you go to the remainder loop. And if it's not, you go into the vector loop, and you may fall into the remainder loop if necessary. Well, there is a lot of control and a lot of loops, and that's not what we want. So the questions, kind of the puzzles that we needed to solve is how do we create one loop for the vector and the scalar code? And we also need to create a hardware loop. So the question was, where do we do this? Before vectorization, during, or after? And how do we actually represent a hardware loop? How do we do this in IR? And then also, how do we lower this? So this is a very brief overview of our optimization pipeline and contributions. The contributions roughly fall into 4 areas: the vectorizer, 2 IR passes, and then a lot of changes to the ARM backend. Very briefly, life of a tail-predicated hardware loop, vector hardware loop starts as a normal scalar loop, which goes into the loop vectorizer. We made tweaks to that, and the result, the output of the loop vectorizer is now a tail-folded vector loop that I showed you before. Then we do quite some heavy lifting on the IR. That's where we recognize hardware loops. So we use the LLVM loop analysis, scalar evolution passes to recognize iteration counts, loops. So in the second box, the output of that is a tail-folded vector hardware loop. Then we have another IR pass that recognizes this tail predication, so that we finally, in IR, have a tail-predicated vector hardware loop, which then goes into the ARM backend, where we do our normal instruction selection and pseudo instruction expansions. And we still have, of course, the tail-predicated vector hardware loop. Then we kind of repeat the things we did on the IR, but now in the backend, we have a hardware loop pass and a tail predication pass. And basically what we do there is we check if all restrictions are met. There are quite some restrictions on actually generating a hardware loop. We check if all these are met. If not, then we revert the changes. We go back to a normal non-hardware vector loop. But ideally, of course, if all restrictions are met, we generate we can emit code. And this was an overview of our pipeline. Sam is going to go into details.
Yeah, so I just want to use the second half to talk about the details of those stages. So we've got 4 stages to go through, and I just want to show you the code and how it is transformed. So the first step is vectorization. We need the vectorizer to do its magic. Obviously, it's going to vectorize, but we also want it to do the tail folding. And that functionality was already existed in the vectorizer, and this would be triggered when you're optimizing for size. So now you can use a command line option to trigger this manually, or you can use a Clang pragma, so the end user can specify per loop if they want this to be performed. And now we're implementing a TTI hook, so the backend can actually specify per loop when this should be triggered. I've put some pseudocode here just to show you what the vectorizer, the logic that the vectorizer will be importing to perform the active lane mask. So we have this loop invariant array of maximum indices, and that is used in the body of the loop with an iCompare, comparing against an array of current indices. So if any of those are larger than your maximum, it is predicated out, it's not active. So after vectorization, we have the hardware loop pass. This is a generic IR, LLVM IR loop pass, and we're going to be inserting intrinsics in and around the loop to designate it as a hardware loop. And we're going to be transforming natural loops with a known trip count, and we'll be using scalar evolution to find that trip count. This pass works on vector and scalar loops, and again, we use TTI to query the backend to see if this feature is supported and whether it is profitable. And the code was originally based on a PowerPC pass, but now PowerPC and ARM use this generic framework. So we have 4 intrinsics. We have 2 that set the loop iteration count, and we use 2 decrement that are used in the loop body for control flow. So the first set loop iteration form, it just takes a value, returns void, so expect this to set some system counter. The second form returns an I1, so as well as setting the counter, you can test that it's not 0, and then we can use that to control whether we enter the loop or not. So 2 decrement forms. The first just returns an I1, so that controls whether you carry on looping or you exit the loop. And the second form returns an integer, so this is the number of iterations remaining. And this really is just a sub. It is an intrinsic that has been renamed. So a concrete example here. In the pre-header, we have our set loop iteration, and that takes 1 operand, and that value enters the loop via phi, and that phi value is consumed by a decrement reg intrinsic, and this returns the remaining number of elements, iterations we still want to execute. That feeds the iCompare, and then that feeds the conditional branch. So all the control flow is handled by normal LLVM instructions. Second example is using the test set form. So the set loop iterations is no longer in the pre-header, but it's in the pre-header's predecessor. So we're controlling whether we're entering the loop or not. So once we have our hardware IR loop, we're going to have an ARM-specific path for MV tail predication. So again, this is a loop IR pass, and then we're going to insert ARM-specific intrinsics. So the first step is that we need to find those loop intrinsics that we added in the first place. We're also going to be looking for master load and store intrinsics, and these will be generated by the vectorizer when it folds control flow or it's done its tail folding. And each of those master load store intrinsics will be taking a lane predicate, so a Boolean vector. And what we want to do is find what that sequence is. It's an iCompare doing something, and we want to replace that with our specific intrinsic. So the pattern that we're actually looking for is this lump of code here. This relates to the pseudo code that I showed in the first slide. And we know the vectorizer is going to generate something like this, so we can literally just pattern match this and replace all this code with one intrinsic call. And this is what it looks like. What we have to do is introduce an extra phi value, and this is going to count the number of elements that we still need to process. So on entry, we're going to have the total number of elements, and we're going to use a sub in the loop to decrease this value. So we've got a vector factor of 4, we're going to sub by 4, and then we know how many elements we still need to process. This value feeds our VCTP intrinsic. You can see this just takes a single value and then returns this active lane mask, a 4 times I1 value. So this is the value that we then feed back to the master load and store intrinsics to perform our predication. So after we're done with IR, we're going to do some code generation. And this is relatively simple. We basically generate a pseudo instruction for any of our intrinsic call nodes. The VCTP instructions, we have a few of them depending on element sizes, and they map one-to-one. One complication here is that we're actually merging intrinsic calls and control flow nodes. So they can be optimized in whatever way by DAG combine. So we need to check that the condition codes and the branch targets are what we expect. Otherwise, code generation goes very wrong. Another thing to note is that for our decrement reg form, we generate 2 pseudo instructions. We've got loop dec and loop end. So that separates out the functionality of performing that decrement and performing the control flow. And that helps, well, it makes our life a lot easier later on, and I'll go into that in further detail. So right at the end of the pipeline is where we're going to do our finalization. So we've done register allocation, we've done scheduling, we've inserted our VPT blocks to perform the predication. And now we need to decide if we're going to generate a hardware accelerated loop or we're going to have to fall back to a generic loop. So whatever we do, we need to expand our pseudo instructions. So we need to decide what we're going to do. Because we expand our pseudos possibly into more than one instruction. So if we're reverting and we can't generate our special instructions, we have to generate, say, a sub, compare, and branch. So the pseudos have to be specified large enough that they cover this case. And finally, we're going to be trying to convert our explicit predication to more implicit. and that is on our to-do list. So we said that sometimes we have to revert, and when does this happen? So I said we have two instructions for this decrement counter, and really when we have real code gen, this is only one instruction. It's also the terminator of the block. So our loop end instruction performs the decrement and it performs the branch. So in machine IR, if anything is using our loop dec value other than loop end, we're going to have broken code because that value does not exist until after the terminator. So this value can be moved around, and it happens because our loop counter is always stored in LR, and the register allocator can use LR, and it does some weird things sometimes. So it can be moved or spilt, so we have to revert in those cases. Sometimes we're operating on a machine loop, and sometimes the blocks haven't been recognized as being part of the loop, so sometimes we don't find our pseudo instructions. So we have to revert because we don't know what we're doing. Another important part is that we have to check that our branch targets are in range. The instructions have quite a generous range. It's like 4K, so it's massive, but our loop start instruction can only branch forwards, and our loop end instruction can only jump backwards. So we have to check that. We also check that there's no calls within the loop. Like I said, we use the link register as our loop counter register. So that's going to get trashed whenever we make a call. The architecture is quite nice. It doesn't require us to do this, but we know we're not going to get any speed improvement from our loop. So we revert there. And the other decision that we need to make is, can we actually do the predication conversion? So we said we've got VPT blocks as the normal way we handle explicit lane predication. And what we want to do is have predication done invisibly, implicitly. So to do that, we need to be able to remove the VPT blocks. So we need to understand the predicates that those blocks are using. This can be complicated because you can have nested conditions within the VPT blocks. So if you can't follow what's making up the predicates, then we're going to be in trouble. We say we have a single register to hold the predicate as well. So if you have some nested condition, this system register we moved into a GPR, it can be modified, moved around, stacks built, whatever. So we need to be able to track this. So we're going to have to implement some kind of data flow analysis on the machine instructions so we can guarantee that the predicates match what our implicit predication is. Also, yes, we have a list of instructions that we think we understand, and we have some that we don't understand. We don't know how they map to the predication. So until we can spend more time understanding our architecture, we kind of just make a blacklist. So we've got two lumps of code here. So the large lump is where we're at, and the smaller code is where we want to be, which is we've seen before. So currently we have the VCTP instruction that's generating the predicate mask. We have that sub, which is tracking how many elements we've currently processed. And we have VPT blocks, so they're the blocks performing the mask loads and stores. So we've got two of them here. And really what we want is to remove those VPT blocks, remove the sub, remove the VCTP. And we get much smaller, faster, and betterer code. So in conclusion, we've got a multi-stage optimization pipeline to have tail-folded vector loops. And code generation for MVE is looking pretty good. And we haven't been working on it for very long, so it's been relatively quick. And that's because we've been able to reuse so much existing code. And the main part that we have to figure out now is this data flow analysis at the machine level. So certainly interested in speaking to anyone else who relies on this level of analysis or transformation. Yeah, and thank you for all your feedback and reviews, if you've gone through any of those. Thanks.
We have time for a few questions.
We do have, okay. I'm Sean Lennon. I'm doing the libmvec talk,
Yeah.
and I emailed you guys. And so the predicate register, does that actually reduce the power consumption?
The predicate register is just, it's kind of a system register.
But if you're doing lanes of vectors, does it actually not do the math if it's masked?
It depends on what the instructions are.
Okay, so, so it can.
Yeah.
And then it seems like, first of all, it seems like libmvec ABI should be adapted so that it can use the predicate register.
Sorry, the what?
It seems like, so there's the libmvec where you can call and do math on a vector instead of just doing a scalar things at a time, and it seems like you could pass the mask to that and not do the whole width of the vector. And then that would also require changing this requirement of doing calls in the loop.
Yeah, so we check for calls. Like I said, we have a TTI hook. So at that point, we try and look through the basic block to figure out if we're going to be making any calls in the first place. So if there's unsupported features, we say, okay, we're going to be generating a library call here. So don't try and do this anyway.
So maybe we would have to maybe put pass the iterator into libmvec as well. I don't know. I would like to see how this could be integrated because
okay. I reckon we should talk afterwards.
Yes.
Yeah.
Any further questions? All right, well, let's thank the speaker.
Cheers. Thank you.